So this is possible if the program has a certain structure. Okay, so let me see if I can write down an example function here. Let's take let's see. So I'm just going to repeat this. And then let's say okay. So you shouldn't worry too much about why this program is like this, right? So the program is like this because I want to give you an example of a vulnerable program, okay? So memcopy is a function, built-in function, right? And it does something very similar to this, right? I just didn't want to write one more loop here, so I'm calling this function memcopy. What it does is it copies, n elements from buff into P. Okay? So what happens here is a little bit more interesting. So let's see. Okay, so let's write down what happens here. So the saved BP is going to look the same. And then the local variable P is going to be allocated. And then this is going to be buff, right? So the array buff, so the same array, and whatnot. Okay. So the important thing here is that the attacker does not, the attacker only writes 101 elements. Okay. So n is going to be set to 101. Okay, which means that the attacker is going to overwrite, up to here. Okay, they're not going to go into either the saved base pointer or the canary. Right. So therefore, the attack so far is not detectable. The second thing that happens is that because the attacker has overwritten P, okay, so P originally pointed to a location on the heap that was allocated using malloc. Okay, but now the attacker has overwritten P, therefore P will point to wherever the attacker wants it to point to. Okay, and in particular, right, attacker can arrange for P to point there. Okay, now when the second copy happens, right, so whatever is the value that is stored here is going to now go sit there.
such a roundabout way if you know what that return address location is anyway? Just
No,
say,
no, you want
Yeah.
to avoid overriding the canary, right? Because if you have override the canary, the attack will be formed,
But then-
and the attack won't succeed.
but then why not just set the pointer to that location already? It seems like you know it.
No, how the attacker? Remember, it's not attacker's program, right? It'll be silly to try to attack your own program, right? Because if you wrote the code, you put your malicious payload in the program. So what you're trying to do is you want to take somebody else's program about you don't have any control over it. It's running on some remote machine. You have no control over it again. That's the attacker. So you have to work with the ability that you have, right? Fortunately for you, the program that you're targeting looks like this, and it has these vulnerabilities that allows you to first override a pointer and then use that to go ahead and modify that. Okay? Because how will you, so all you have is this code, right? Remember, this is the code you can execute. There's nothing else. So there isn't a magical way to just modify this, because in order to do that, you will need to have written the code of this function, right? But what executes is exactly this code. And you need to make sure that when this code executes, it will achieve your objective as an attacker. Any questions? Okay, so this is how you kind of jump past the canary, right? So this way you're able to override, and this is called okay. So essentially you're overriding. It's called either a double override or double pointer override, so that you first corrupt a pointer and then you use the corrupted pointer to overwrite your real target. Right? So essentially, your real target is being corrupted in 2 steps. Yeah.
So if you save the return address, how can you do that?
I'm sorry. So canary is a random value.
You cannot save the return address in memory.
So are you suggesting to change the design of the canary so that what it is a second copy of the return address, right? So that doesn't help, right? Because then the original attack would still work. The attacker has to do what? Exactly, right? So that doesn't help. So, right, good.
So how would the pointer know that it's a file?
So again, remember what's happening. When the attacker first overrides from here, right? So the attacker has overwritten the pointer P, and the attacker knows what is the location of the return address, right? So that's how they put that value over there.
How would the attacker know the address of
So again, that is a requirement, right? The attacker needs to know, or else none of these will work, right? So the attacker needs to know exactly the layout of the runtime memory at the time of attack. Okay, otherwise none of these attacks work. Is there another question there?
So we're just making the assumption that the attacker knows, but we're not talking about how the attacker knows here.
Right, correct. So
Okay.
the attacker has to know that the program is like this, right? They need to know exactly what the program does. They also need to know exactly where the stack is allocated in memory. In particular, when this function executes, where does its stack frame reside? Okay, so they need to know all these details. Okay, without that they cannot perform the attack. Okay, so typically, remember what happens usually is that if you it's the same program that runs typically the attacker can get access to the program, right? Because the program is rarely a secret, especially if you're talking about the binary version of the program. It's available to everybody, right? So the attacker can take this program, run it on their own machine, and then they can look at what is the memory layout at that point, right? If that memory layout is exactly the same on some other machine, which is often the case, then there is none of, knowing exactly where things are is no longer a difficult thing to do. Okay? So that's one way the attacker can get around. Okay? The second way for the attacker to get around is called so at least in this design, right, the save base pointer is here. Okay? Don't think of the double pointer attack. So you don't even have to think about this program. You can go back to the old program which didn't have this. Right? So you can just say, okay, it's no longer here, no longer there. Okay? Even without that, what you can do is you need not go all the way to corrupt the return address. Instead, you can just corrupt the saved base pointer. Okay? So what would that allow you to do? What would be the purpose of corrupting the saved base pointer? So, how will that happen? So the attacker needs to be able to control either the execution of the program or some data used during the execution of the program. Right? So that's what the attacker's goal is. Preferably, they get to change the control flow. Less preferable, but still acceptable, is that they can control some critical data. So what can you do if you control the saved base pointer? Okay. So think about what happens when the function returns. Right. So you haven't corrupted the return address, right? And you haven't changed the canary, so the return is going to go through fine. Okay? Which means that the corrupted base pointer is going to become the base pointer for the caller, right? Because the function, when it returns, it's going to set the base pointer to whatever value is stored here. So if the attacker controls the frame pointer from the caller, right? Notice that everything, all the local variables and parameters, right, are accessed as using an offset from the base pointer. So the attacker controls the base pointer. They can make the base pointer point to some region of memory that they control, which means that they will be able to control the values of local variables and parameters. Right? So if, let's say, the code has, if the caller had something like let's say this is so system is a function that you can call in C to execute a command. Right? So it's basically S will be a shell command, right? So it will be given to a shell, and the shell will execute the command S. Did I use? Yeah. So typically, what might happen is that okay. So what the program does is there is a string variable that's initialized to the name of some command that this function G wants to execute. So that initialization happens here, and then it calls F, and then it calls, system S to execute that shell command. Okay. So now what the attacker has done is, by corrupting the saved base pointer, the attacker is now able to control what S means. Okay? Because S is going to be accessed using something like, you know, something like this, EBP minus 1 or some offset like that. Okay? So if the attacker controls EBP, this system S is going to be nothing but whatever is at EBP minus 1. And if the attacker controls EBP, then the attacker can control EBP, whatever is the value that's stored in EBP minus 1. Okay? So this way, the attacker can control the command that's going to be executed here. Right? So again, depending upon how your vulnerable program is, the attacker may be able to carry out their attack without affecting the return address by simply overwriting the base pointer. Okay? So these are some of the attacks that can succeed in spite of having a canary. Okay? So of course, when you realize that these attacks are possible, then you go back and say, can I improve my canary design so that these attacks don't succeed? Okay? So you think of ways that you can improve this to avoid this base pointer attack.
Put the canary after the base pointer.
Right. So avoiding this attack is quite easy. You simply say, I'm going to put right? Okay. Now, what about the double pointer attack? Can you do something to prevent that?
Basically, you have to fix the buffer sizes of the inputs that you are having.
Well, that's something that you have to rely on the programmer to do, right? So programmers make mistakes. Because if you assume the programmer can be, trusted to get their programs right, then I guess, this course itself probably wouldn't exist, right? So the reality is that, because of complexity, there exist bugs in software and you can't get rid of them. And so you have to assume that this type of programs exist and this kind of double pointer override is possible. The question is whether the canary can be designed in such a way, or the canary-based protection scheme can be designed in such a way that you can prevent that attack from succeeding.
Encode the return address with the random value, something like that.
So that's kind of a separate approach. There is something called an XOR canary, right? So the idea of an XOR canary is that you don't have a canary over here, right? But instead you put the canary, you simply XOR a random value with return address, and that's what you store. Okay? So the idea is that when you enter the function, you're going to XOR the return address that's on the stack with a random value, okay? And then before you return, you're going to again XOR whatever is stored here with that same value again. So you remember that, if you right? So if you take any value, XOR it with any value, and then you XOR it again with the same value, then you should get the original value, right? So this is a way of protecting the return address, because if the attacker does overwrite the return address, what's going to happen in this case is the program is still going to, XOR that whatever the attacker wrote there with the random mask X, and so now it'll basically jump to some random place, right? Because if you take a valid return address and XOR it with a random value, it's going to point to some random place in memory. Typically, a random place in memory will not have code, So essentially that will cause the program to abort. Okay, so that's called an XR canary. There are a couple of reasons why it's not used, it's not that popular. One of them is it still leaves the base pointer open to attack, right? And secondly, there are, when you do, there are many, so for instance, debuggers will get confused, right? Because debuggers think, the stack contains a bunch of stack frames and the return addresses. So when a debugger prints you some kind of stack trace, okay, that's based on knowing that return address is over there and it has a certain value and so on, right? So if you XOR it with a random value, then it becomes difficult to for the debuggers to work. And it's not just the debugger, because many times when your program crashes at runtime, you get a stack trace, and that wouldn't work either. So there are compatibility reasons as well why the XOR canary is not used. Instead, this kind of random canary in the middle of the stack is what is used. Okay, so we already have the design of canary that protects the save base pointer. Now let's go back to the question: is there any way to protect P? Okay, so that's all right. So there is a simple way to protect P, which is to say, I won't allocate P over here. Okay, so I will put P over here. Okay, so now if you override, now you are not going to be able to corrupt P. Right. So the idea is that all of the array type variables will appear above, and all of the non-array type variables will appear below, right? So this is sort of, so there is this design called so there is a design called Propolis, which is the name of the system, and the paper that introduced the solution called it Propolis. But right now, this is what you see being implemented in every compiler out there, and that is the scheme where you put the canary after the save base pointer, you put all the arrays over here, and the non-array variables are allocated here. And when you do that, you are able to deal with most of these attacks. Okay, again, not everything,